Alright, so let's start the transistors. Transistors are three terminal devices, that means they have got three terminals basically. So till now what we have learned is two terminal devices, for which means they have got two ends. So resistor has got two ends, battery and then capacitor and then diode, zener diode, even in inductor, which means we connect, which it has got one terminal here, one terminal here. Now transistors are three terminal devices, they have got three terminals, one here, one here, one here. So there are three connections to be made here. uh, One of the terminal is called the emitter terminal, other is called the collector terminal, and the middle one is always called the base terminal. Now the bipolar junction transistors, these bipolar junction transistors, BJTs, they are of two type actually. One is called the NPN, another is called the PNP. That the name is given on the basis of how we fabricate them. So if we have here the emitter side, so what we have here in BJT is two PN junctions. So it is P, N and P regions, or N, P and N regions. You know what are the P regions and N regions, isn't it? Because we already covered that in diodes. So this P region is called emitter, this P region is called collector, and the middle region is always called the base. So here the N type is base. So this is a PNP transistor. And what about the NPN? Well, this is the N side which is emitter, this is the N side which is collector here, and then this is the middle one is always the base. There are two properties of base, which is first that the base is made very thin. As you can see, the length of the base is here, even in the diagram, very small, thin base, and the base is very lightly doped as compared to the emitter and collector. So these are the two properties of base that you should remember. Now out of this two P's on the extreme sides, outer sides, so one P is one P type semiconductor, one P type silicon will be the emitter. Now emitter is heavily doped, lots of P's here, P type impurities, whereas the collector is moderately doped. Again, this collector here in the NPN will be moderately doped with the N type impurities, whereas the emitter will be the heavily doped. Collector is also the longer as compared to emitter. So these are the three different two differences between the emitter, base and collector. So emitter heavily doped, collector moderately doped, base very lightly doped. Extremely thin, very small length of base, moderate length of emitter, and large length of collector. So this entire P type is called emitter, entire P type, and this emitter, where we connect the emitter to the external circuit, this is the metal contact here. So and then this is the where the external circuit will be connected to the emitter. The point at which the external circuit is connected to this emitter, this is called the emitter terminal. Similarly, we have base and collector terminals also. So PNP and NPN transistors, very simple stuff. This is what is written here. Now in the circuit diagram, how do we distinguish whether this P side is the emitter or this P side is the collector? Rather than writing here the emitter and writing here as the collector, what we do is we put an arrow in the emitter. So wherever you see this is the terminal, one of the terminal, this is the another terminal, and this is the third terminal here. So in this emitter terminal there is an arrow put here, again in the emitter terminal there is an arrow put. Now the arrow will be put either like this or like this. So remember, whatever is the arrow represents the emitter, and no arrow means the collector. Middle one is obviously always the base. Now how do we put arrow? So this way of putting arrows helps us to identify whether the transistor is a PNP type or NPN type. The arrow indicates the direction of the forward current that will flow when the base emitter junction is forward biased. So if you see here, this is PNP, and this PNP to forward bias, we should connect a battery like this, isn't it? So this PN junction forward bias, and the current will flow like this. So if you can see, then in the forward bias condition, the current is entering the emitter. Since the current is entering the emitter, we draw the arrow like this, which represents the current entering the emitter in case the emitter base is forward biased. Similarly here NPN, So if you forward bias this PN junction, this is the emitter and this is the base. So to forward bias this PN junction here, this PN junction, we should connect the battery to the P type, positive terminal of the battery to the P type, negative terminal to N type. And how will the current flow? Current will flow like this, isn't it? And now the current is leaving the emitter, so it is coming out of the emitter. So this is the emitter, it is coming out of the emitter. So this arrow represents the it signifies that the transistor is of NPN type. So NPN versus PNP. So that's the difference. So remember these two terminologies. These are the circuit symbols for the transistor, PNP and NPN. Now transistor working. To understand the transistor working, we should understand something called the transistor action. Now to understand the transistor action, we should first understand how the current flows in the PN junction. In fact, there are three currents or three types of currents in the PN junction forward bias. So let's discuss first about the three kinds of currents in the PN junction. Actually, there are only two types, but still I have, for the explanation purpose, considered a three type. So first is a very simple electron current. So whenever this PN junction is forward bias, you remember the PN junction is forward bias, isn't it? So there are lots and lots of electrons onto the N side here in the conduction band, and these electrons, they diffuse onto the P side, and these electrons will be sucked by the battery here and then put it in here. So electrons, they complete the path, and this is what is the electron current. There is an electric field of the battery which is helping the electrons to move like this in the left direction from here to here. So you know that the barrier height is decreased, the diffusion increases. Barrier height is decreased, the diffusion increases, and the forward current is established like this. So one of the component of the forward current is this comprised of the electrons, electron movement. So this electrons of the conduction band here. Then comes the hole current. So lots and lots of holes in the P type. So hole current here. So positive charges will move like this in the direction of current. This is how the current will flow clockwise, and so holes will also move in the clockwise direction. So holes will diffuse from P side to N side because lots and lots of holes here. So holes going here, these holes will be collected by the battery and then dumped here into the high potential. The holes will go again like this. So this is what is a hole current. Now if you are not comfortable with hole current, because we know that holes are basically vacancies, so you can consider them as electron currents also. Only thing is that these electrons will not be in the conduction band, these electrons will be the valence band. In fact, the movement of electrons in the valence band is what is the actual hole current, isn't it? So lots and lots of holes onto the P side. So electron coming here and then going like this and then going like this is equivalent to holes moving in this direction. So holes moving like this means electrons in the valence band moving like this. Electrons will be pulled up by the battery, which means battery will supply holes. Electrons will be pulled up, electrons will be dumped here, which means holes going here like this, and this electron coming here again into the valence band will go like this into the valence band. So valence band, from valence band electron, again battery, valence band electron, again battery, valence band electrons, again battery. And what was there previously? Sorry, not this one. Previously it was all conduction band electrons, battery, conduction band electrons, battery. So this is what is called as the electron current, and this is what is called as the hole current. So now comes the recombination current. What is recombination current? Recombination current, you might have already actually we have already discussed this during this LEDs. So what happens is that these electrons, this slide was already covered, but just to recap, electron coming here, they are into the conduction band and then they jump into the valence band and they move into this valence band. So from the electron in the conduction band, they go into the valence band and then the valence band here it moves. So movement of electrons in the valence band is called the hole current. So there is a partial hole current from here to here, and there is a partial electron current because of the electrons movement. So on the N side there is electrons movement, on the this side there is a hole movement, isn't it? And then through the battery only the electrons flow. So this is just for understanding purpose. Let's see here, very important. For example, there is a current which is established in the forward PN junction. This is P type obviously, and this is N type, and this is a positive terminal of battery, this is negative terminal, and the current is flowing like this. So this is what is the direction of the conventional current, I coming back, Now let's say this current is established because of the flow of 100 electrons. So 100 electrons are coming like this, and the battery is dumping those 100 electrons here like this. Now let's say out of 100 electrons, this 30 go into the valence band and 70 are in the conduction band. So this 30, 30, 30. Now out of this 70, 10 have combined with the holes. And so this electrons go here like this. And these electrons, after combining with the hole, because they have gone into the valence band, they will go from one hole to another, and these electrons will keep moving. So 30 electrons were already in this valence band here moving leftward, and 10 additional have come. So how many are total remaining here is 40 electrons like this. So instead of saying that 40 electrons are moving towards left, we can say that 40 holes are moving towards right, whereas these 70 electrons which were traveling from the n side, only 60 are remaining in the conduction band. If you take any cross section, how many electrons are anyway crossing is 60 plus 40 is 100, or 70 plus 30 is 100, isn't it? So this entire thing can be divided into three categories. What is that? Category number one, we can say that this 60, 60, 60, 60. So 60 conduction here, 60 conduction here, 60, 60 here, 60 conduction, 60 conduction. This is all purely electron current. Then 30 here, 30 here, 30 here, 30 here. So this 30, 30, 30, 30 is just a whole current, isn't it? And then the last one, this 10 here. So this 10, 10, 10, 10 here. This 10 in the conduction band, then 10 going down, recombining, filling into the holes, and then moving from one hole to another like this. So this electrons here. So this is called the recombination current, because here the current is happening, and recombination is a part of this current. Now, so if you have understood these three types of current, purely electron current in the conduction band, purely hole current in the valence band, and then partial electron current in the conduction band and partial hole current in the valence band. If you are okay with this, let's move ahead with the transistors. Now what will happen in case of transistors? Which of these three currents will be there, and which will not be? So let's check the transistor working. So we will discuss both the kinds of transistors always, so you can always skip some parts of lecture. If you have studied or understood one kind of transistor, the other kind of transistors will be like exactly opposite. I mean, we'll discuss about it anyway. So considering this NPN transistor, so what we have done here is, this is emitter, base and collector. Emitter, as you know, is heavily doped, and base here is very lightly doped. And what we have done is forward bias this emitter base PN junction, and simply we have connected the base and collector with just a wire. So the base collector PN junction is unbiased, short circuited. So as soon as this is forward biased, isn't it? This is a forward bias PN junction. What happens in case of forward bias PN junctions? In case of forward bias PN junction, lots and lots of electrons will be diffusing onto the n side, and lots of holes will be diffusing onto the electrons will be diffusing onto p side, lots and lots of holes will be diffusing onto n side. You know that diffusing of holes from p side to n side is like diffusing of electrons in the valence band from n side to p side. Now here the holes which will be diffusing from p side to n side will be negligible. If you see in the previous case, we said that the 30 electrons are diffusing in from the valence band of n side to the valence band of p side. So 30 electrons here into the valence band, which means 30 holes here. But here we could take this 30 holes, but how many holes are there actually in a base? As we remember, the base is very lightly doped, so the holes that will be diffusing onto the n side will be negligible as compared to the electrons which are diffusing from n side to p side. So that hole current is gone. Now that we know only these electrons will be diffusing from n side to p side here, so these electrons have got two things to do, two options. First, they can combine with the holes and form the recombination current as we have discussed so far, or they can go ahead forward. See, there is an electric field anyways, isn't it? This electric field will anyway accelerate the this is the direction of force on the electrons, and this is the direction of electric field of the battery. This is E of the battery here. This battery's electric field will anyway accelerate the electrons, so electrons either can recombine here or they can go ahead with the collector and come back like this. Now how many electrons will be actually able to recombine with the holes here? So As we know that the base is thin as well as lightly doped. So two things are there. First, the availability of holes in the base region is very small, so the recombination that will be happening is small. Secondly, the base is made very thin, so the electrons will be spending very less time in the base region, and they will be moving quite fast because the region is very thin or very small. So within no time they will be again going into the collector, and so the probability that those electrons actually combine with the holes in the base is very small. So majority goes here, and those majority which go here, they come back like this and they go again here, and some of the electrons combine with the holes here, and since they combine with the holes here, so this electron will be like this, isn't it? Just if you remember the hole current, how is the recombination current? In the recombination current, the electrons recombine, they travel within the holes and then go through the battery like this. So the same thing happening here. These electrons, they recombine with the holes, travel within the holes, come from here and then again put here. So this electrons which are actually able to recombine with the holes here, that will constitute this base current which will come from here. Why it is called base current is because it is coming out of this base terminal. So this electron are coming like this, so current will be like this. So let's call it IB, the base current, and the current which is flowing because of the electrons going into the emitter terminal, isn't it? These electrons are going into the emitter terminal. Sorry. So these electrons will constitute the emitter current, and the electrons which are coming from here are coming out of this collector terminal, and this will constitute the collector terminal. So as I have told you that the recombination happening is very small, recombination current which will actually be the base current is very small, and so we can understand that out of these three, these two are negligible. Which two are negligible here? In case of thin and lightly doped base, this recombination current is very small, and this hole current is also very negligible. What dominates is this electron current only in NPN transistors. So this is just an example here. Assuming that the 100 electrons going here, out of 100, 99 come here and 99 return like this, and only one combines with the hole here, and it goes like this and to the battery here. So corresponding to this one electron here, there will be a base current like this. This is the base terminal. Corresponding to 99 electrons coming here, there will be a collector current, and corresponding to the electrons going like this into the emitter, there will be current like this, isn't it? The current, conventional current, is opposite to the direction in which the electrons are moving because electrons are negatively charged. Okay, so if you apply the junction law here, what we get is that the emitter current is equal to the base current plus the collector current. Now this is applicable for all the time, and this is a very important formula which is applicable without any limitation or exception. Now what we do is define two things which are called alpha and beta. These are the two ratios. So one of the ratio is the collector current by emitter current. So this is IC by IB. See, whatever electrons are coming here, that will constitute these electric currents, and majority of these electrons are going into the collector region without recombining with the holes in p type. So majority of the electrons which are constituting the emitter current are also going to constitute the collector current. So most of the emitter current, which means 99 or more than 99% also of the emitter current, will be actually collector current. So this collector current by emitter current will be alpha, and alpha will be close to 1. And then what we do is define another ratio, which is the collector current by base current, which is the ratio in which the emitter current is getting divided. So IC by IB, which is beta. Now we know that the most of the emitter current is collector current, and only a small part of the emitter current is the base current. And so this base current is very small, collector current is quite high, so the ratio is very high actually. There is a relationship between alpha and beta. So we know that from the junction law, we divide both the sides by IC, and from this we know that this is 1 by alpha, this here, and we get the relationship by rearranging. Very important relationship, and some questions are generally asked in mains or some other competitive exams like medical also, in which directly one of the beta or alpha is given and other is asked. Now for a particular transistor, beta is fixed. So beta will depend on the doping concentrations also, isn't it, and how thin we have made it. For example, if we make the hole very thin and very lightly doped, then beta will shoot up. isn't it? So beta depends on the doping level and it is fixed for a transistor during its operation. Alright. So constant are always valid when the transistor is in active mode, and yeah. So another point is that the ratio of IC by IV is equal to beta is valid only for the transistor working in active mode. We'll discuss the three modes of transistor working: the active mode, the saturation mode, and the cutoff mode later. But just remember that the ratios are valid only when it is in active mode. So question is, I is equal to 20 milliampere, beta is equal to 98. What is required is to find out IB and IC. So as you can see this, and then so IC by IB is equal to beta, which is 98. So IC is equal to 98 beta IB, sorry, IC is equal to 98 IB. So just putting IC is equal to 98 IB, so we get IB, and then IC can be calculated from this. So this is just a simple question, and these kind of questions are also asked in mains as well as your NCERT exam. So don't take this lightly, isn't it? Very simple thing. All right. Just go through it, whatever is written. Okay. In case of a transistor, we divide the entire circuit into two parts. One is called the input part and one is called the output part. So see here, this is a NPN transistor, and this part, which is the emitter to base, like this part is called the input side and this part is called the output side. So this current is called the input current and this current is called the output current. So this output current is 99.99% of the time output current is collector current. And what is that collector current consisting of? Collector current consists of the electrons which are coming from the emitter. So this collector current is governed by how many electrons are coming from the emitter side to the collector side and without recombining with the holes in the base region. So we can say that this collector current is controlled by emitter current. And what does the emitter current depend on? Emitter current depends on this battery, isn't it? This is like a PN junction, and this is PN junction is a forward bias. So you know the forward bias characteristics of a PN junction are like this. So the more and more the you forward biases and higher is the current that you get. So emitter current is controlled by this battery. This battery will apply electric field and it will drive these electrons to go from here to here. It will force them and these electrons will come into the collector. So collector current controlled by emitter current controlled by this battery here. So this battery controls the collector current. This is what is called the transistor action. So here the output is controlled by the input voltage. This input voltage, this one. This is called VBE. Why? Because it is the potential difference between the emitter and the base. Emitter and base, EB, BE, whatever. Okay. Moving on. Now till now, what we did is we just connected this PN junction of this base and collector. See, base is P, collector is N, so definitely there is a PN junction. What we did to this PN junction? Did we forward bias or reverse bias? Nothing. We just simply short circuited it, and we came to know that whatever electrons are coming from emitter to the collector, they will be simply pulled away by this battery here and then dumped into this again. So nothing very special. Now what if we put another battery here between this PN junction, which is the base and collector? What will happen? So let's discuss if we forward bias this collector base PN junction also.